Hello everyone, it's Mrs. Hanson here. We're beginning our journey together in our class looking at thermochemistry, the first module in lesson 1, with our learning goals of defining energy and distinguishing types of energy, describing the nature of energy changes and that accompany those chemical and physical changes. We're going to be able to distinguish the related properties of heat, thermal energy, and of temperature. We'll define and distinguish specific heat and heat capacity and describe the physical implications of both. And finally, in our first section of thermochemistry, we'll practice performing those calculations involving heat, specific heat, and temperature change. In this beginning part of our video, we'll talk about energy. Let's begin. So we'll begin by simply defining the term energy, and in your notepad at the top it says, what is energy? And I'd like you to simply write energy, a classical definition here, is the capacity to do work. Energy comes in two different forms. If energy is the capacity to do work, we look at two classes of energy, what we call potential energy and what we call kinetic energy. I'd like you to define potential energy as the energy that is stored. The energy of position is another way to define that. Now in chemistry, potential energy is that energy that's stored within a chemical bond. And when we break bonds, and that's what chemistry is all about, energy is released. A second category is known as kinetic energy, and I'd like you to define that as saying it's the energy of motion. Anything moving possesses kinetic energy. We call this the law of conservation of energy, which is a law in thermodynamics. It simply states we cannot change the amount of energy in the universe. We cannot create it. We cannot destroy it. All we can do is let it change from one form to another. The law of conservation of energy says the total energy in a system does not change. Energy is conserved. Energy can change from one form to another. But the amount of the energy in the universe is constant. So a great example of potential energy, and I know this is archery, which is coming up in the Summer Olympics, pulling back that arrow, pulling back the string on the bow and having the arrow ready to launch. When that position is as far back as that lady can possibly pull, she's got potential energy stored in that bow. And of course, when she releases that, you have that now in motion, all of this stored energy in this particular, the string being pulled back is then released and the arrow goes forward. So stored or position, and then of course the motion creates kinetic energy. And I like this diagram too. Here we are at the very top of a roller coaster hill. So 100% is stored energy, the energy of position, gravitational energy here. And then of course you start to go down the hill. About halfway, you have half kinetic energy, half potential energy. And at the very bottom of the hill, 100% kinetic energy because there's no energy of position any longer. So at the top of the hill, stored energy, and when you're in motion, kinetic energy. When you think about this law of thermodynamics saying we cannot create nor destroy the amount of energy in the universe, we only allow it to change from one form to another. These are examples of those types of energy. Potential energy in chemistry is the energy stored in bonds. Kinetic energy in chemistry is stored in bonds. Kinetic energy in chemistry is thermal energy, the energy of moving particles, such as heat flow from a hot object to a cold object. There are other types of potential energy, such as elastic. Remember that bow that we talked about in the previous slide? When she pulled back the string, she was storing energy due to tension. There's other types, such as nuclear. You blast apart a nucleus of an atom, all kinds of energy is released. or gravitational potential energy, like at the top of the hill in the roller coaster. Kinetic energy includes thermal, mechanical, electrical, sound, and electromagnetic waves. All of those on the EM stands for electromagnetic spectrum. All of those are in motion. So if we're studying energy, specifically in chemistry, it will be stored in bonds or released or absorbed as heat. So our focus, of course, is chemical bonds. Chemical bonds store potential energy. And a compound with lower potential energy is more stable than a compound with higher potential energy. That is just really a natural law. It says compounds want to be at the lowest energy possible. And I think about the natural state. I think all of us want to be at the lowest energy level possible, especially with our 8 a.m. chemistry class. Then we see that reactions that form products having lower potential energy than reactants, they're actually favored. So what that means just visually, here's energy on the, just kind of draw this with me if you will on your margin. Here we have just an XY axis where we can see on the Y axis is energy. And we'll learn that energy is going to be measured in joules or in calories. Calories might be a more familiar term just from food intake is measured in calories. And in the metric system, we'll write down joules. But you can see as energy is increasing on the y-axis, and you can just think of this as time. Time goes by and reactants turn to products. You call that progress of a reaction. If the reactants have this, just kind of an arbitrary line that I draw, a starting amount of energy, and we'll learn that there's this little energy barrier that separates reactants and products. We'll learn that this is called activation energy. And again, we'll redraw this several times because we'll have this energy barrier that here I'm going to abbreviate EA as the activation energy. And as time goes by, the reactants turn to products. And you can see then there's a difference in the amount of heat content, the amount of energy between the reactants and products. The reactants are of higher energy than the products are down here. And we'll see that heat is released. And this is a more stable configuration because they are of lower products. We will learn that this will be called exothermic, heat releasing. And when bonds break and new bonds form, heat is being released, energy is being released, and we'll measure that energy using bond dissociations. So these units of energy I've been saying, one is known as a calorie, and you can abbreviate that with a small c, or some people will write out CAL for calorie. We define that to be the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a small case calorie, how much energy needed to raise 1 gram of water 1 degree Celsius? That is also known as the specific heat of water. And you should know that the specific heat we'll learn is a kind of a definition for this. And it just says the specific heat of water, you can say, is 1 calorie. It takes 1 calorie to raise 1 gram of water by 1 Celsius degree. And so in the metric system, there is another unit of energy. Now in America, we're used to the English system carrying calories of energy, but we should also be familiar with the metric system. The unit of heat energy is known as the joule. And this is actually an honorary name from a physicist whose last name was Joule. So you'll see that was a capital J when we write out its unit. A joule is another unit of energy. So you could say the specific heat of water in a joule is 4.184. That's the conversion between a calorie and a joule. It takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. The equivalent values between calories and joules should be memorized. You'll need to know those conversions, so I'll just encourage you to remember 1 calorie is equivalent to 4.184 joules. So both joules and calories can be reported in larger units. So these are actually kind of small calibrations. When I say 1 calorie, it's kind of a small number. So joules and calories are more often reported out in kJs, kilojoules, and kilocalories, kcals. So just thinking that through, we know that kilo means 1,000. So it takes 1,000 joules to equate to 1 kilojoule. It takes 1,000 calories to equate to 1 kcal, a kilocalorie. And so we can equate these two as well. A kilojoule and a kilocalorie would have the same conversion as a calorie to joule. 1 kcal is equivalent to 4.18 kilojoules, kJs. So let's kind of bring that out to practice. Let's practice converting between heat units. You'll need a calculator for this part of your lesson. Perhaps pause your video if you've not yet grabbed your calculator, or perhaps you're used to having a calculator every time we start with chemistry. But this is the bottom of page 1 where it says let's practice converting between heat units. And I pulled this right out of your text. A reaction releases 421 kJs of energy. How many kilocalories does this correspond to? So we're working to memorize our conversion that we equate 4.184 kilojoules is the same as saying 1 kilocalorie. So let's begin by writing what was given to us, 421 kJs. And remember our conversion, what is it that we want over given so that our unit will cancel? We were given a kilojoule. I want to make sure it cancels, so it must go on the bottom. And I want to end with a kilocalorie, so it needs to go on the top. So we end with it. Our conversion says 1 kilocalorie is equivalent to 4.184 kilojoules. So this looks like a divide by problem. And let me pull my calculator out. Let's hit this together. I have 421 divided by 4.184, and my screen reads 100.621, and it goes on and on and on. Let's consider sig figs. I have 3 sig figs here, so my answer should also have 3 sig figs, so I'll round to 101 kilocalories. That's not too bad, is it? Let me ask you to try some on your own. Please pause the video, work to create mastery, right? So the more you practice on your own, the more proficient you become. You're turning the page in your notepad to the top of page 2. Come back to the video when you're ready to check your answers. Pause, work ahead, and then come back. That's me turning the page. In letter A, we started with 42 joules, and we wanted to go to calories. Remember what we want over given for our conversion. We want to switch to calories, and we were given a joule. We know that our equivalent values, 4.184 joules, is the same as saying 1 calorie. So you divided. You said 42 divided by 4.184, and you found 10, and your screen said 10.038. But remember, we're considering sig figs, so I'm going to write 10 with a decimal point to make sure that's 2 sig figs, and my unit there is calories. 55.6 kcals, 2 calories. So what is it that we want? we want a calorie given a kcal down below. Whoops. So I think about want over given. It takes 1,000 calories to equate to 1 kcal. So we're moving our decimal place 3 spots over. So when I write that out, 55600. Now I think about sig figs. This is the number of calories. I'm only allowed 3 sig figs in my final answer. And right now I have ambiguous zeros. So if I don't leave as, no decimal point, because I don't want those zeros to be significant, I'll still have only 3 sig figs. So 55600 with no decimal point gives me the correct magnitude of the number and still 3 sig figs. I did place a decimal point here to ensure I had 2 sig figs, so that one was needed. I'm kind of reviewing our sig fig rules. 326 kcals to kjoules. So here I want my kilojoule and I need to cancel the kcals. 4.184 is our conversion between the land of kilocalories to kilojoules. So 326 times 4.184, and we get a value that says 1363.984. We need 3 sig figs. So this fourth number here is looked at, and it is not up high enough to round. So 1360, that's 3 sig figs with no decimal, kilojoules. Letter D, 25.6 kcals times, let's see, we want joules. I need to go, so this is a good one. We need actually 2 conversions, don't we? Because our conversion says a kcal to a kj, I can get there. And so I have to give myself a little more room. So let me just rewrite that answer. Yeah, this will work for us. We want kcals. And so therefore, to cancel kcals, it takes 1 and 4.184 kjs, and I can easily convert from a kj to a j. And by doing that, we know it takes 1,000 joules to equate to a kilojoule. So this involved 2 transfers. Kcals canceled in the first step, kjs canceled in the next step, and we'll finally land to joules. So to hit that, 25.6 times 4.184 times 1,000. And my screen has a really big number. It says 107110.4 joules. We have to equate that to 3 sig figs. There's 3 there. So 3 sig figs, 107000, no decimal. And that way I'll have 3 sig figs in my final answer. So I have the correct magnitude, the size of the number is correct, and I have 3 sig figs reported. Good work. There's some more. A combustion of gasoline releases 11.5 kcals of energy. So that's the number of kilocalories for every gram of the gasoline that's burned. How many kilojoules of energy are released? How many joules does this correspond to? So the 1 gram is telling us the amount of energy, but it really doesn't play a role in the calculation. It's giving us kcals of energy, and we want to know kilojoules. So we can use our conversion where we know 1 kcal is equivalent to 4.184 kjs. And we can get our first part of the answer by simply multiplying 11.5 times 4.184. Did you find 48.116? And then we'll consider proper use of sig figs, so we'll round 48.1 to get 3 sig figs, and that's a kJ. How many joules does this correspond to? Well, that's just changing out our kilojoules into just simply a joule. And we know kilo means 1,000. So there's 1,000 kilojoules or 1,000 joules in 1 kJ. That means we're going to take our decimal and move it 3 spots to the right. So that becomes 48100 joules. No decimal point, so I can retain 3 sig figs. How are you doing? These aren't bad at all, especially after coming off of stoichiometry. I'm sure these are nice. Now, where can we apply this?
Let's turn our attention to a topic on specific heat.
Another quality of solids is a physical property known as specific heat. Specific heat is defined as the amount of heat energy needed to raise of any substance by 1 Celsius degree. This goes back to our chapter 6 a little bit when we learned about calories and joules. Calories and joules, we said 1 calorie was the same as 4.184 joules. And we defined really the specific heat of water at that time. We said it takes 1 calorie of energy to raise 1 gram of water 1 Celsius degree. Or in the metric system, we defined it as saying it takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. I'm telling you the specific heat of water when I'm giving you that information. But every substance has its own unique value of specific heat. Just like density. Density is unique to each and individual compounds or elements. It is an intensive property that gives us the quality related to, if you remember, density is mass over volume. This is a property, just like specific heat, unique to each individual compound. And the reason we're bringing it up here is we can study specific heats of metals. So specific heat, the larger the number, the value, the magnitude of the specific heat, it takes more and more and more and more energy to raise the temperature of 1 gram of a substance by 1 Celsius degree. So if I put in a little bit of heat, it doesn't move very much on the temperature scale. So if you compare, say example, 4.184 joules per gram degree Celsius is that specific heat for water. And let's say I have a metal coming in at 0.2 joules per gram degree Celsius. Adding the same amount of heat, the water hardly warms up at all, and the metal will get really hot really fast. Here are some examples of specific heat of substances. In the left column, these are all examples kind of just written out here. We have aluminum, 0.214 calories per gram Celsius. See that calorie unit? Or in the metric system, a joule per gram degree Celsius. Remember the conversion. 1 calorie is 4.184 joules per gram degree Celsius. And you can see that right here. That's the very definition of water, right? That's our base of the system. So we can just see a list of all these different substances, and the term specific heat is applied to them, telling me how many calories of energy or how many joules of energy it would require to warm up 1 gram of that substance by 1 Celsius degree. And if we want to calculate, we can consider calculations in terms of the mass, the specific heat, and the change in temperature. Let's do some thinking together. Considering the elements aluminum, copper, and gold. So just a moment ago I had this screen up, aluminum, copper, and gold. I think this is in your notepad for your convenience, but just so I didn't have to go back and forth on the slide, I wrote them down here. Aluminum, copper, gold, and here's iron, just from the table on the previous slide. Aluminum has a value of 0.214, copper 0.09, gold 0.03, and iron 0.107. Those are in calories per gram Celsius. What if you put in 10 kcals of heat to each of these elements, same amount? What element would have the highest temperature? Which one would warm the most? What do you think? Which one has the lowest specific heat? The one that doesn't take much energy at all to convince it to warm up. Looks like gold. The gold specific heat is 0.0310 calories per gram degree Celsius. So thinking about how much would it raise if I added 10 kcals? A lot. And which one would hardly move at all? Which one is the biggest specific heat number? Aluminum would be this 0.214. And again, just comparing, this is the smallest specific heat value. This is the largest specific heat value, meaning that this element, gold, would change temperature the most. Which element would require the largest amount of heat to raise it by 5 Celsius degree? And that's going to be the largest one, right? It's going to take a whole lot of energy to get aluminum because it has the highest specific heat value. The higher the specific heat, the more energy it takes to raise it by 1 Celsius degree. The larger the specific heat, the less the temperature of a substance will change when it absorbs energy. The larger the specific heat, the more heat that must be added to increase the temperature of the substance. And that's what we just wrote on that previous slide. Well, let's introduce a formula to how to calculate specific heat. We can calculate heat released or heat absorbed. Heat absorbed we know to be endothermic. Heat released is to be exothermic. Heat is measured in calories or it's measured in joules. The heat unit is a calorie. We can calculate that by taking the mass times specific heat times the change in temperature. Heat gets a letter Q for a symbol. I don't know why, but Q is given to heat. M stands for the mass measured in grams. Delta T stands for the change in temperature. And just think about what that means. You would find a change in temperature by knowing its initial and final. So T final minus T initial is how much it changed by using a thermometer. And then you're going to get the specific heat, and it's given a little letter C. The specific heat is the other variable in this equation. And that's the unit then, this could be in Celsius degrees or in Kelvin, because when you subtract, you're going to get the same difference. If I subtract two numbers on the Celsius scale, I would get the exact same answer if I had subtracted those values on the Kelvin scale. So it doesn't matter if we're in Kelvin or Celsius here. If my heat is measured in a calorie, my unit for specific heat is calorie per gram degree Celsius. If it's measured in a joule, it's joule per gram degree Celsius. So we're just matching units. Q is equal to MC delta T. That is our formula for calculating heat. I have this nice little tool that helps me remember. Draw this with me and it will help you with the algebra. Here's Q on the top And I can find Q by multiplying M times C times delta T. And this allows me to use this little visual where I can cover up the variable that I want to solve for and see the relationship to the other. So cover up Q, just cover this up and you get M times C times delta T. If I want to solve for specific heat, cover this one up and you get Q over M times delta T. So it's just a little, a little tool, a little visual to help us remember the algebra. Q on the top is found by taking mass times specific heat times the change in temperature. Shall we try one? How many calories are needed to heat a pot of water from 25 degrees Celsius to 100 degrees Celsius? I'm going to make that bigger. Q is equal to M times C times delta T. We're being asked for calories, so this is what I want to know. That's the one I'm going to cover up. I have 1,600 grams of water, and my temperature change will be the difference from, here's your initial, here's your final. So delta T is 100 minus 25, which is 75 degrees Celsius. We'd like to know Q. Well, you know it's not given on this page, but we're expected to know it. What is the specific heat for water? Now I know that I gave you a table, but this is one that you should really just know. Know this one. 4.184 is equivalent to saying 1 calorie. So it's 1 calorie per gram degree Celsius. That's what I have to know right here. 1.0 calorie per gram degree Celsius. So I want to know Q. I'm going to find that by multiplying M times C times delta T. 1,600 grams times 1 calorie per gram degree Celsius times our delta T, which was 75. Notice how grams canceled? Do you notice how Celsius canceled? And when we multiply M times C times delta T, you found Q. And Q comes out to be calories of energy. So we're just going to take 1,600 times 75 degrees Celsius, and we get a big number. How many zeros is on your screen? 120,000? And there's your answer. 2 sig figs? That will work. How'd you do? Shall we try another? How much energy is required to heat 28 grams of iron from 19 degrees to 150 degrees? Report your answer in calories and in joules. My formula, my little helper, Q is equal to M times C times delta T. What do we know? Well, we were given 28 grams. I can place that here. That's the mass in grams. The temperature change, initial was 19, T final was 150. So the delta T was 131 Celsius degrees. We want to know energy. That's Q. How much energy? That's heat energy. And the C, the specific heat constant. Well, again, I gave you this chart. You do not have to memorize all of these elements. Don't think that for a minute. But I do expect you to remember water because it is the basis of that whole metric system. But what I did was just kind of clip art for us iron, since it was the, I just pulled that from the chart. Now in a calorie, we'll use 0.107, and in a joule, in a second calculation, we'll have to use 0.448. So heat measured in calories, we'll use 28 grams times 0.107 calories per gram degree Celsius times our change in temperature of 131 degrees Celsius. Grams canceled, Celsius canceled, and we arrived at calories. 28 times 0.107 times 131. My screen reads 392.476, and let's just make sure we give that, looks like 2 sig figs. Shall we write 390 calories? What about in joules? Q measured in joules would still have 28 grams, same mass, same temperature change, but what will be different is the specific heat. We have to make sure we grab that in a joule per gram degree Celsius, but the same temperature change. See what we've done? Grams canceled and Celsius cancels, and we're going to end with joules of energy. Let's hit that. We have 28 times 0.448 times 131. My screen reads 1643.26, but let's do that to 2 sig figs. 1600 joules. M times C times delta T are units to help us find heat energy. So now, remember, our little helpful hint here, Q is equal to M times C times delta T. And let's just fill these in as we read it. It says 400 calories of heat. That's this variable. We're given Q this time. Of 25 grams, that's a mass unit, of propanol at 21 degrees. Well, this is the initial temperature. We're being asked to solve for the final temperature. So this is what we want to know. I need to figure out how much it changes by so that then I can figure out where it will land. So 2 propanol in calories. That's this number right here. So this time we know Q is 400 calories. I want to know the specific heat. So I have 25 grams times 0.612 calorie per gram Celsius, and that's going to give me my delta T. So this is what we want. You see what we have? Q over M times C. Q over M times C. That's going to pull out delta T. So hit that with me, your key sequence. 400 divided by parenthesis 25 times 0.612, close parenthesis. Now my screen reads 26.144. Well, just right there is fine. Now that's not my final answer. That's my delta T, how much it changed by. If we're adding heat means it's going to warm up. And think about that. If the initial temperature started at 21 degrees and it warms up by 26 degrees, I'm going to keep the 2 sig figs we need anyway. Right? Added to means it's going to warm up to the final temperature. Right? This will be a bigger number because I'm warming it. So it's going to land at 47 degrees Celsius. It changed by 26 degrees Celsius, so it would end at 47. We're taking the initial and adding the change to find the final. Think about what I just said there. TF minus TI is delta T. So if you just think about what we said, you're going to just rearrange that and say to find the final, it's delta T plus the initial. And that's how we found 47 degrees Celsius.
Here's the next one.
Pause and think this through. Give yourself a little think time and try this problem out. Come back to me when ready. We have two separate problems here, don't we? We have to solve for copper and then for mercury. I know that Q is equal to M times C times delta T. We want to know the final temperature, so we better solve for delta T. That's what we want to know. Now both of these are giving me 20 calories of heat, and they're both giving me 10 grams, but I've got to solve two separate problems. One using the copper and one using mercury. So let's set up for copper first. With copper's value of 0.09, this looks like my math. Delta T will be solved for by taking our 20 calories and placing it over our 10 grams times the specific heat of 0.09 calorie per gram Celsius. This is your Q, this is your M times C, and you're solving for delta T, right? This is the one you want, so you cover it up and you see the algebra, Q over M times C. So let me hit that for us. We'll have 20 divided by parenthesis 10 times 0.09. And I hit, and it says 22.22 degrees Celsius. Now if it started at 15 degrees Celsius, and you added heat, the new temperature will be 22.22 degrees higher than 15. So I'm going to just add those two together, and the final thermometer will be 37.22. I'll just leave, that's close enough, 37 degrees Celsius for copper. What about for mercury? Its delta T would use the same 20 calories, the 10 grams that you had, but now remember mercury has a different specific heat, so 0.0335 calorie per gram degree Celsius. Remember that in a parenthesis down there. Remember, we want to solve for temperature, so you see your formula, Q over M times C. 20 calories divided by parenthesis 10 times 0.0335. And this time the delta T came out to 59.7 degrees. If the initial temperature was 15 degrees, the final temperature is simply adding those together. So while I have 59.7 on my screen, I'll just add 15, and this would end at 74.7 degrees Celsius. So clearly the mercury warmed up significantly compared to the copper.